Chapter 14 is on alcohols, ethers, and thiols. Alcohols are compounds containing an oxygen bonded to a hydrogen, which is called a hydroxyl group, and that is bonded to a carbon with 4 single bonds, as shown in this diagram here. This is our carbon bonded to the hydroxyl group. This carbon has all single bonds attached to it. We can also look at our diagram on the left, which is a model of our alcohol. And we can see the carbon here is bonded to the hydroxyl, and that has all single bonds attached to that carbon. To name alcohols, we follow the same rules as alkanes with these additional rules. The longest chain must include the carbon connected to the hydroxyl group. The suffix OL represents the hydroxyl group. We will replace the ending E in the parent name with OL. So for example, I have C bonded to 4 hydrogens. The name of that compound would be methane. Now the compound next to it, we have the OH attached, our hydroxyl, so that makes it an alcohol. So in order to name that, all we've done is dropped the E at the end of methane and added the OL, and this is called methanol. Name these compounds. The one on the left, we have 2 carbons, all single bonds to hydrogen, so it's an alkane. The prefix is eth for 2. The ending is ane for an alkane. So we have ethane. On the right, we have our alcohol because we have the hydroxyl group present attached to a carbon with all single bonds. So in order to name this, we have the same prefix eth, and then ethane, we drop that E and we add an OL. So that's called ethanol. Our third rule for naming alcohols is when assigning numbers to the carbons in the parent chain, assign the lowest possible number to the carbon attached to the hydroxyl group. The number for location of the hydroxyl groups takes precedence over other groups. The one on the left, we have 3 carbons attached to a hydroxyl. So 3 carbons, if it was an alkane, would be propane. So we write propane, but we drop the E and add OL. So that is propanol. And now this is saying where we're going to assign the number to the carbon where the hydroxyl is attached. So we could count left to right or right to left from one end of the chain to the other. We're assigning the carbon attached to the OH to the one that has the smallest number. So that's going to be at carbon 1. So we will not use the numbering at the top. So to name this compound, we would put a 1 in front of propanol. The 1 tells us the location of where that hydroxyl is attached. So it's 1 propanol. The one on the right, same thing. We have 3 carbons, so it's propanol. And now the location of where the hydroxyl group is attached is in the middle one, which is carbon 2. It doesn't matter which end we count from, it's the same. So this one's called 2-propanol. I have a review question at the bottom. Are these 2 compounds constitutional isomers? So review on a constitutional isomer are molecules that have the same molecular formula but different structures. So let's look at the molecular formula. The one on the left, we have 3 carbons and we have 8 hydrogens and 1 oxygen. The compound on the right has 3 carbons, 8 hydrogens, and 1 oxygen. So the first rule in determining a constitutional isomer is same molecular formula. I would say yes. The second rule is, do they have different structural formulas? They do have different structural formulas because they have different names. You can't have 2 different names for the same compound. So checking the names is one way we know. Different structural because of where the hydroxyl group is attached. The first one's attached at carbon 1. The second one, the hydroxyl is attached at carbon 2. So yes, they have different structural formulas. So we can now answer our question. We satisfied both rules in determining constitutional isomers. Yes, these two compounds are constitutional isomers. Name this compound. We're going to start by finding the longest chain of carbons that's attached to our hydroxyl group. So we can count across the top, and we have 4 carbons straight across. And we want to count the carbons so that the hydroxyl group is attached to the carbon where it will have the smallest number. So originally I went left to right. Let's try going right to left. And if we do right to left, our OH is attached to carbon 1. So that's the numbering scheme we want to use, not the numbering that was at the top. So if we have 4 carbons, that would have came from butane. So we're going to drop the E and add OL. So we have butanol as our parent. The hydroxyl is attached at carbon number 1. So number 1 goes in front of butanol. Now in this case we have a group attached. Our group is called an ethyl. So the child is going to go in front of the parent, ethyl butanol, and we want to show the location of where the child is attached to the parent, and that's at carbon 2. So we put a 2 in front of ethyl. So the name of this compound is 2-ethyl-1-butanol. Name this compound. Let's start by finding the longest chain that includes the carbons that are attached to the hydroxyl group. So in this case, we can go straight across and count our carbons. So we know how to name our parent. So we have 7 carbons going straight across. So the name of the parent would have been heptane. We drop the E and add OL, so it's heptanol is the name of the parent. We want to show the location of where the hydroxyl group is attached in front of heptanol. This is attached at carbon 2. We can see if we counted from the other direction, it would have a much larger number. It would be a carbon 6. So we're going to include the OH attached at carbon number 2. Now we have 2 groups attached. We have 2 methyl groups. And when we have 2 of the same groups, we put di in front of that. So we have dimethyl. And then we want to show the location of where these groups are attached to the carbons in the parent chain. So the first one is attached at carbon 2, and the second one is attached at carbon 5. So we put 2, 5 dash in front of the dimethyl 2-heptanol. So the name of our compound is 2, 5 dash dimethyl dash 2 dash heptanol. Rule number 4 for naming alcohols is for cyclic alcohols. The carbon bonded to the hydroxyl is always going to be carbon number 1. It's not necessary to show the number 1 in the name because that will be a given. You're going to number the carbons in the ring to give the lowest numbers to the other groups. So in this compound, we have our hydroxyl attached to a carbon in a ring. That's going to be carbon 1. We're going to number the carbons so the groups will then have the smallest number after 1. So if we go left to right, we would have groups at positions 2 and 3. Our total number of carbons in our ring is 6. So let's start by naming the parent. 6 carbons in a ring is going to be cyclohexane. Drop that E and add OL to tell us we have an alcohol. So we have cyclohexanol. And we know that the OH is attached to carbon 1, but if it's in a ring, we don't have to show that 1. So now we want to show the location of our groups and name our groups. So we have 2 methyls. So that will become dimethyl. And they're located at carbons 2 and 3. So the name of our compound is 2,3-dimethyl cyclohexanol. Draw 3-propylcyclobutanol. But tells us we have 4 carbons. Cyclo means they're in a ring. So let's draw 4 carbons in a ring, which gives us a square. We can attach those together. And then the ending OL means we have a hydroxyl group attached. And then it tells us at carbon 3, we have a propyl attached. So carbon 1 is going to be the carbon where the hydroxyl is attached. So we're going to count around our ring to carbon number 3, and we can add a propyl, which is 3 carbons, as a group. And then we want to add all of our hydrogens. For our propyl. And then the last thing we want to do is add the hydrogens to our parent, because we always want to make sure carbon always has 4 bonds. So this is our drawing for 3-propylcyclobutanol. Rule number 5 for naming alcohols is compounds with 2 or more hydroxyl groups have the ending diol, triol, etc. You are only going to be asked to name alcohols with either 2 OHs or 3 OHs attached. I will not ask you for any more. So I'm going to cross off, etc. Please take note that the last E is not dropped from the parent name, as we did for alcohols when there was only 1 hydroxyl attached. So the first example we have here is we have 2 carbons with single bonds, so that would be called ethane. Now we're leaving the E. If it had just 1 hydroxyl, we would drop the E and add OL. But because we have 2 hydroxyls attached, we're going to add the ending diol. The E is left primarily in there for pronunciation. So we have ethane diol. We want to show the location of the 2 alcohols, so they're going to be on carbons 1 and carbons 2. So we call that 1, 2 dash ethane diol. The common name is written below here, is ethylene glycol. I do want you to know the common name for this compound, besides being able to name it following IUPAC rules. Ethylene glycol is one of the components in antifreeze. That's a cooling agent in your car. The next compound on the right is we have 3 carbons in our parent chain. So that would be propane. And we have 3 hydroxyl groups attached. So the ending will be tri for 3-ol. So we have propane triol. Now we want to show the location where our hydroxyls are attached. They're at carbons 1, 2, and 3. So we put our numbers in front of the parent name. So the name is 1, 2, 3 dash propane triol. Common name for this one is glycerol, and that's a sweetening agent. So I do want you to know the common name for 1, 2, 3 propane triol as well, which is glycerol. Name this compound. This compound is a cyclic alcohol. We previously learned if you have 1 hydroxyl group attached to a cyclic compound, that's going to be carbon 1. But if we have 2 or more hydroxyls attached, as we do in this example, you're going to need to show the location in the name. So in this case, we're going to have carbon 1, 2, 3, 4, 5. So our hydroxyls are attached at carbons 1 and 2. We'll need to put that in the name. So remember, if 2 or more hydroxyl groups in a cyclic alcohol, you need to show numbers in the name. So 5 carbons in a ring is cyclopentane. And because we have two or more hydroxyl groups, we leave that E and we add the ending diol to represent that there's two hydroxyls. And the location of my hydroxyls are at carbons 1 and 2. And then I have a group attached, a methyl. And methyl is attached to carbon number 3. So the name of my compound is 3-methyl-1,2-cyclopentane diol. Rule number 6 for naming alcohols is for unsaturated alcohols. Unsaturated alcohols contain a hydroxyl group and a carbon double bond. So they actually have two functional groups in that compound. The hydroxyl group takes precedence over the carbon double bond for numbering the carbons in the parent chain. To name, we're going to show the carbon double bond by changing the AN in the parent to an EN, and to show the hydroxyl group, we're going to change the last E in the parent to an OL ending. We'll show the OH location as a number inserted in front of the OL. So let's look at our first example. We have 3 carbons. So 3 carbons, if it was an alkane, would be called propane. Now our rule says we've got a double bond, so we're going to change that ending to an E, so that would be propene. And then, because we have an alcohol at the end, the hydroxyl, we're going to drop the E and add an OL. Now we want to show the location of where the hydroxyl group is attached to which carbon and where the double bond is attached between two carbons. So the precedence goes to where the carbon is attached to the OH. So this would be carbon number 1, carbon 2, and carbon 3, because we want carbon 1 to be where the hydroxyl group is attached. Now to show where that is attached, let me write the name down below again. I said we're going to insert in front of the OL. So it's propan 1 all. And then the location of the carbon double bond is between carbons 2 and 3, so we put a 2 in front. So that compound is called 2-propan 1 all. The one below, we have 1, 2, 3, 4, 5 carbons, and we're going to count in both directions to see which carbon gives the hydroxyl group the smallest number. So if we go from right to left, our hydroxyl is at carbon 2 versus left to right, it's at carbon 4. So we're not going to use the numbering that I wrote at the front. I'm going to erase that. So if we have 5 carbons, the parent's name is pentane. If it's single bonds, we have the double bond, so it's pentene. We drop the E and we add an OL. But we want to show where the hydroxyl is attached, so we put carbon 2 in front of the OL. And then we need to show the location of the double bond, which is between carbons 3 and 4, so we put a 3 in the front. So that 3 is telling us where that double bond is located, and the 2 tells us where the hydroxyl is located, which is given by the name OL. So the name of the bottom compound is 3-pentane-2-all. Let's start by drawing the structure of ethanol. F, the prefix, tells us we have 2 carbons. The ending, OL, tells us we have an alcohol, which means we have a hydroxyl group attached to one of our carbons. And then we're going to saturate it with hydrogens. So this is our structure for ethanol. So we learned how to name alcohols and how to draw structures. Now I'd like you to know some information about some of the alcohols. The first one, ethanol, is also known as drinking alcohol. This is the alcohol in alcoholic beverages such as wine or beer. Ethanol is also a solvent for medicine and perfumes, meaning that it's the liquid that's going to dissolve your active ingredient. So you might find that in NyQuil or in different types of perfume. It's also used as an antiseptic to kill germs. Ethanol can be produced naturally by fermentation, or synthetically you could make it in a laboratory and end up with the same product. The fermentation process is shown below here. For fermentation, you need to start with sugar. And if you were making wine, you would start with grapes, and grapes contain the sugar. Zymase is an enzyme that is found in yeast. So you need yeast and you need sugar to create alcohol. So undergoing our chemical reaction, the zymase converts the sugar into ethanol, and we also produce carbon dioxide in the process. So if you were making wine, you would allow the container to be open to let the carbon dioxide be released. If you were making champagne, you can close the lid and have your basically carbonated wine. If you were doing beer, you might start with grains that contain sugar, and the same process, the zymase would convert the grains into alcohol, and your beer would be bubbly because you have the carbon dioxide, which is a gas. Now the yeast die when the concentration of ethanol gets to be above 13%. So that's why your wine, generally it's not going to be higher than 13% because your yeast naturally will die when they have that much alcohol in the system. Beer and wine generally contain about 3 to 4% ethanol. Prior to 1200 AD, only beer and wine were available for drinking. In about 1200 AD, distillation was developed. Distillation is a process to obtain a higher percent of ethanol concentration in your alcoholic drink. So this shows us our distillation apparatus. In the distillation flask, we would put wine, and we could heat up the wine with the Bunsen burner, and wine contains water and alcohol. We could be more specific and say ethanol. That might be, about 13%. So it's about in the smaller amount. The boiling point of water is 100 degrees Celsius. The boiling point of ethanol is about 78 degrees Celsius. So distillation is a process to separate mixtures based on different boiling points. So when we heat the wine up, the ethanol is going to boil first. So the vapors come up here. They go across this column that is surrounded by a condenser where there is cold water coming in and going out. So it cools the vapors back to the liquid phase. So we're able to get what we call our distillate or our hard alcohol at the end. So this would be how you could make distilled spirits or hard alcohols such as whiskey. So your hard alcohols are usually labeled as proof to tell you the percent of alcohol in the hard alcohol. Proof is double the ethanol percent. So whiskey that is 86 proof means it's half of that amount alcohol, so it'd be 43% alcohol. I do want you to know the definition of proof. So if I ask you a question such as, what is the percent of ethanol in 90 proof vodka? It would just be half of 90, and that would be 45% ethanol. Generally, your hard alcohols contain between 35 to 50% ethanol. But obviously, the highest proof you could get would be 200 proof, and that would be 100% ethanol. Drinking alcohol is produced by fermentation/distillation by law. And this is primarily just regulatory reasons. As I said, you could produce ethanol in the laboratory, but all of the drinking alcohol that you would buy, your beer, wine, or your hard alcohol, is all going to be produced by either fermentation and or distillation. Here is one way you could synthetically produce ethanol. If I start with this compound, we have got 2 carbons with a double bond. We can name that Eth is my prefix for 2, ene is the ending for the double bond. So if I react ethene and water, and I must do this in the presence of sulfuric acid. Sulfuric acid is not actually incorporated into the product. It's what we call a catalyst. It makes the reaction go forward. And then I can produce ethanol. So this ethanol would be the same as if I produced it by fermentation, or if I produced it in the laboratory. Now, again, the ethanol that you would be drinking for drinking alcohol has to be made by fermentation and then undergoing possibly a distillation process. This ethanol is going to be much cheaper than the ethanol you're going to buy at a liquor store because of all the taxes added onto it. So in the chemical industry or the pharmaceutical industry, they use what we call denatured alcohol. Denatured alcohol means it's ethanol that you can synthetically make with a little bit of methanol or benzene added to it. If you were to drink this, it will make you sick. Okay? It's used, as I said, in industry to produce other chemicals. So it could be used by the chemical industry, the pharmaceutical industry. A lot of companies use denatured alcohol because it's going to be much cheaper than buying alcohol produced by fermentation. So I used to work for a pharmaceutical company, and we would buy it in these large 55-gallon drums of ethanol. But again, it was denatured alcohol. So if an employee thought, I'm going to take this home and have a party this weekend and mix it with punch, everybody would get sick because methanol and benzene are both toxic compounds. So it's nothing you would want to drink. This reaction shows how ethanol is metabolized in our body. So if you drink alcohol, how does it get out of your system is what we're looking at. We're starting with ethanol. Ethanol reacts with an oxidizing agent, which could be oxygen or other types of oxidizing agents in your body. And this undergoes oxidation, which means the addition of oxygen to a compound or the removal of hydrogen from a compound. So in this case, we're removing hydrogen from our compound and we form acetaldehyde. Acetaldehyde undergoes further oxidation and breaks down the acetaldehyde into other products such as water and carbon dioxide that can be excreted from your body. There is a drug called disulfiram, also known as antabuse, and this is a drug that is sometimes given to alcoholics. Disulfiram prevents the oxidation of acetaldehyde to other products. So basically in our reaction, the antabuse stops the reaction at this step right here. So then the acetaldehyde builds up in the bloodstream, and that causes nausea, vomiting, and sweating. So the idea is if someone was an alcoholic and they take this pill, disulfiram, and they want to have a drink, they know that by taking antabuse, it's going to cause them to become extremely sick if they start drinking alcohol. So that's the idea. Is mentally, you don't want to make yourself sick. Methanol is when we have one carbon bonded to a hydroxyl group and then single bonds to hydrogen. Methanol is used as a solvent for paints and shellacs and varnishes. It's also used as fuel in certain race cars. Methanol is also used to make formaldehyde, as shown in this reaction. So methanol undergoes oxidation and forms formaldehyde. Formaldehyde is an embalming fluid that you may have experienced in a biology class. If you were to ingest methanol, it would undergo oxidation in your body and also produce formaldehyde, which is very toxic. So methanol is something you would never want to drink. It's a very toxic compound. In fact, if you were to drink just 15 milliliters, that would cause blindness. If you drank 30 milliliters, which are pretty small amounts, it causes death. So also know with the alcohols, which ones are toxic and which ones are not toxic. So methanol is definitely a toxic alcohol. Let's draw the structure for 2-propanol. Prop means we have 3 carbons. The OL tells us we have a hydroxyl group. The 2 tells us it's located at carbon 2. So in the middle carbon, we have a hydroxyl group, and then the rest of the carbons will be saturated with hydrogen. The common name for 2-propanol is isopropanol, and you may have also heard of rubbing alcohol that you may have in your medicine cabinet at home. So some of the uses for 2-propanol are to cool your skin by removing heat when it evaporates. Sometimes this is used to reduce fever, and basically how that works is it reduces the size of blood vessels near the skin surface. Rubbing alcohol can also be used as a disinfectant for cuts and scrapes. It can be used as an astringent. It hardens your skin and decreases the pore size. 2-propanol or rubbing alcohol is also used as a solvent in the cosmetic industry and for perfumes and for different skin creams. 2-propanol is also a toxic alcohol, so this is not an alcohol you want to drink. The next alcohol we're going to learn about is ethylene glycol. This is a common name for an alcohol that I want you to remember. This is the structure for ethylene glycol. Let's name it following the IUPAC rules. We have 2 carbons, so that would be ethane. We have 2 hydroxyl groups, so we add diol to our parent. The hydroxyl groups are attached to carbons 1 and 2. So we put 1 and 2 in front of ethane diol. So the name of ethylene glycol following IUPAC rules is 1,2-ethane diol. Ethylene glycol is found in antifreeze, which is put in your car radiator. It works by lowering the freezing point of water. So the idea is you put antifreeze into your car in cold weather to prevent the engine from freezing. This is a toxic and viscous liquid. So if you spill anything on the ground, you want to clean it up immediately. Pets have been known to drink ethylene glycol or antifreeze because it tastes sweet, and they have ended up poisoning themselves. So you want to be really careful with that. In 1937, a tragedy occurred. There was a pharmacist who wanted to take this little yellow pill called sulfanilamide. This was used during the war to treat infection, and it worked really well. So he took this little yellow pill and he crushed it up, and he wanted to be able to give it to children. So children have a hard time swallowing pills, which is why he crushed it up. He added ethylene glycol as his solvent to dissolve the crushed up powder. He added some red food coloring and some cherry flavoring so that children would drink it. By adding the liquid to it, that's when we call this an elixir. So mothers were giving this elixir sulfanilamide to their children who may have had ailments like the common cold. It ended up killing 107 children before they realized the cause was having ethylene glycol as your solvent in this drug. And ethylene glycol attacks your organs, so unfortunately these children suffered a horrible death. In 1938, the FDA, the Food and Drug Administration, created the Food, Drug, and Cosmetic Act. This act was created that required companies to test food, drugs, and cosmetics before they could be sold to the public. Prior to that, food, drugs, and cosmetics did not have to be tested. So that's what happened with this elixir sulfanilamide. It was not tested before it was given to the public. And the pharmacist did not plan to kill these children. He did not realize that ethylene glycol was a toxic liquid. He ended up committing suicide because he felt so bad of what happened. Glycerol is the common name for this compound below here. Let's name this compound following the IUPAC rules. We have 3 carbons, so it would be propane. We have 3 hydroxyl groups, so that would be triol. And then the hydroxyl groups are attached to carbons 1, 2, and 3. So we would put 1, 2, and 3 in front of our name. So the name of glycerol is 1,2,3-propane triol. Now, glycerol is a non-toxic alcohol. It's a viscous liquid. It's used as a sweetening agent, so you may find it in granola bars. It's used as a lubricant for glassware in a chemistry lab. It's also used as a moistening agent in lotions and cosmetics. And it's used to make nitroglycerin, which is an explosive, as shown by this reaction below. So here we have glycerol. We're reacting it with nitric acid. This is in the presence of sulfuric acid, which acts as a catalyst to make the reaction go. And then we produce nitroglycerin. Nitroglycerin is an explosive, so it was used for blasting hills and used during wartime. It was very dangerous. Alfred Nobel, a Swedish chemist who you may have heard of before, the Nobel Peace Prize is named after him. Created dynamite, it's kind of ironic, in 1866. And how he created dynamite is he took nitroglycerin, which is a liquid, and he absorbed it into diatomaceous earth, which is like a white powder. And then he put a fuse in it, so it was more controlled than nitroglycerin. So it was a big improvement for safety that we could still have this explosive dynamite, but you could control it. And the reason why he created it is his brother was killed in a factory that was making nitroglycerin. The whole factory actually exploded. So he was doing something to make the world a better place by creating dynamite. We are going to learn how to do oxidation reactions of primary and secondary alcohols. Oxidation is the addition of oxygen or removal of hydrogen. Primary alcohols are alcohols when we have a carbon that's attached to a hydroxyl group, and that carbon is directly bonded to only one other carbon. That makes it a primary alcohol. So primary alcohols will react with an oxidant to form an aldehyde. That aldehyde will be oxidized to form a carboxylic acid. In this reaction, we have ethanol, which is a primary alcohol. It's reacting with an oxidant, and in this case, it's losing 2 hydrogens, and then we form an aldehyde. It undergoes oxidation further. In this case, we add an oxygen and we form a carboxylic acid. In the laboratory, we sometimes do an experiment where we will take alcohols, primary, secondary, and tertiary, and try to determine if they will react or not. The oxidizing agent we use is potassium permanganate, known as KMNO4. This is a purple liquid. This purple liquid, if it undergoes oxidation with our compound, it will turn black. That way we can tell if our alcohol reacted. Ethanol is found in wine. And if wine is left open to the atmosphere, it undergoes oxidation. And when it undergoes oxidation, the ethanol turns into an acid, which is found in vinegar. And the name of the acid that's formed is the compound here is called acetic acid. Secondary alcohols will react with an oxidant to form ketones. So here we have 2-propanol. And this is a secondary alcohol because the alcohol is attached to a carbon that is attached to two other carbons. And our secondary alcohol undergoes oxidation by losing two of these hydrogens, and it forms the ketone. And in the lab, we can do the experiment with the potassium permanganate, the KMnO4, as our oxidant. And if it goes from purple to black, that means we had a secondary alcohol. Now, we would not be able to tell the difference between a primary or a secondary alcohol when we did this lab, so we would say it's either primary or secondary. Tertiary alcohols are when we have a carbon that's bonded to a hydroxyl group that it's attached to three other carbons. That makes it a tertiary alcohol. Tertiary alcohols do not react with oxidants. So there would be no reaction that occurred. So in the laboratory, we can identify if we have tertiary alcohols. If we had a number of different alcohols we were testing, primary, secondary, and tertiary, tertiaries are the ones that do not change color. So they start purple and they stay purple. That's how we can identify which ones are tertiary alcohols. Ethers are functional groups. An ether is when we have an oxygen bonded to two carbons, as shown below here. The general formula is sometimes given as R bonded to oxygen bonded to R prime, where R and R prime can be the same or different groups, as shown below here. R in this case is CH3, R prime is also CH3. Now again, your R prime could be a different group. Maybe it might be CH2, CH3, so it can be the same or something different. So the main thing to realize is to be able to pick out a functional group. So let me draw the structural formula for the one ether here. So it's clear to see that the oxygen bonded to carbons on both sides, that would be my functional group, an ether. To name ethers, first you're going to name the groups, then add the word ether. If your two groups are the same, your R and R prime, use the prefix di. So CH3 is called a methyl. The other group attached in our ether is a methyl. So to name that, we have two of the same group, so we would have dimethyl, and then we write the word ether to show what kind of compound it is. Name the following compounds. First, we're going to name the group. So CH3 is methyl. The other group is ethyl. So to name our compound, we're going to put our group names in alphabetical order. So it would be ethyl, methyl, and then our functional group is the ether. So it's ethyl, methyl, ether. The next one, we have an ethyl group and another ethyl group. So we have two of the same group. So we write diethyl ether. Diethyl ether is known as ether. It was developed in 1842 and was first used as a general anesthetic. This was a huge discovery because prior to 1842, patients would undergo surgery and have a successful surgery, but many times they died due to shock because they weren't using an anesthetic. Some of the disadvantages of ether is that it's slow acting, it irritates the respiratory tract, and it causes nausea. However, ether was used for about 100 years before they developed new anesthetics. Other anesthetics are now used, such as enflurane and isoflurane. These are common names that you don't have to know. I'm also not going to ask you for the IUPAC names because we haven't learned how to name those groups here. What I might ask you is which ones are ethers. So it's picking out the functional group. So in the first one here, again, we need to imagine this hydrogen can be pointed up or downwards. And so this oxygen is directly bonded to that carbon and then to another carbon. So this one is an ether on the left. On the right, we can clearly see we have a carbon bonded to an oxygen bonded to another carbon. That one is also an ether. Here are two more anesthetics, common names halothane and nitrous oxide. Which ones are ethers? Well, none of these have carbon bonded to oxygen bonded to another carbon, so neither of these are ethers. But we could do some practice naming these following our IUPAC rules. We have two carbons in this compound, so the parent would be ethane. And then we have groups of fluoros, and we have a bromo and a chloro. So we want to put those in alphabetical order. So bromo comes first, then chloro, and then we have three fluoro, so we're going to put trifluoroethane. And then we want to show the location of our groups. So this will be carbon 1, the first one, carbon 2, the second one. So it's 1-bromo-1 chloro, and then 2, 2, 2. I'm going to insert that there. Trifluoroethane. So the IUPAC name for halothane is 1-bromo-1-chloro-2-trifluoroethane. And this is an anesthetic that's used in veterinarian medicine. The one on the right, nitrous oxide, is sometimes called laughing gas, is used in the dental field. We could name that compound following our rules that we learned how to name covalent ionic compounds. This would be a covalent compound because we have two nonmetals. So we for name N is just the element name is nitrogen. The second one is oxygen. We change the ending to "-ide". Covalent compounds have prefixes, so that would also be known as nitrogen dioxide. Here are a few of ether's chemical properties. Ether is inert, which means it's not very reactive. So ether is actually very useful as a solvent because it's not reactive. One of the primary reasons that ether is no longer used as an anesthetic is because it's very flammable. And it's also easily oxidized by air to give explosives. So ethers must be stored in a sealed container away from light and heat. And usually they're stored in a brown bottle so that the light does not cause them to react, and away from heat so that they don't explode or start a fire. Thiols are a functional group that are compounds that contain an SH group, which is known as your thiol, bonded to a carbon with 4 single bonds. So it's similar to our alcohols, where we had the OH bonded to a carbon with all single bonds. This would be a sulfur attached to a hydrogen, which is attached to a carbon that has all single bonds. So the general formula here, we have R, that would represent carbon, and then we could have multiple other carbons or other elements attached to that carbon. Thiols often have foul odors. For example, this thiol below is the odor that gives us the skunk smell. And we can see that this is a thiol because we have the sulfur bonded to a hydrogen, and then that's bonded to a carbon here with single bonds. And then we have some other carbons attached to our compound as well. To name thiols, we're going to follow the same rules as alkanes with these additional rules. The longest chain must include the carbon connected to the SH or thiol group. You're going to add the suffix thiol, this represents our SH group, to the end of the parent name. Don't drop the final E. You want to show the location of the thiol group as far as showing the number of which carbon it's attached to if you have more than 2 carbons in your parent compound. So let's name this compound below. We have 3 carbons, so the parent's name is propane. And then we have the thiol attached, so that becomes propane, thiol. And we want to show the location because our parent has more than 2 carbons, and that's going to be carbon 1 that's attached to. So that would be called 1-propane thiol. This is the compound that gives us the odor in onions. Name the following compounds. So the first compound, we have 1 carbon, so the name is methane. And we have our thiol attached, so it's methane thiol. We only have 1 carbon, so we don't have to show where the thiol is attached. It can only be attached at carbon number 1. This is the compound that gives the smell to oysters. The next compound, we have 2 carbons, so the name is going to be ethane. We have a thiol as our functional group, so we include that in the name. It's ethane thiol. And again, 2 carbons, we don't have to put a number in the front to show where that thiol is attached, because if it's attached at either one, it would still be carbon 1. And ethane thiol is the compound that's found in natural gas. Now this is the compound that's added because it smells. So methane, which is what natural gas is, does not smell. This is an extra compound that's added to it that if you have a gas leak, you're going to smell that. So your smell from natural gas is actually due to ethane thiol.